Welcome back, guys. So next we have packet-based flow control. Here we have to first break down messages into packets and then interleave these packets on links, thus improving the link utilization. Unlike circuit switching, the remaining techniques will require per node buffering to store in-flight packages. So the first in line is store and forward. Here we need to allocate links and buffer to entire packet. Head fleet waits at router until the entire packet received before being forwarded to next hop. So this store and forward mechanism is not suitable for on-chip networks. It requires buffering at each router to hold the entire packet. Thus, packet cannot traverse the link until buffering allocated to entire packet. So it incurs high latencies, pays serialization latency at each hop. Serialization latency is the time it takes for a packet to be serialized for transmission on a narrow channel such as cable. So a narrow channel is a channel where there are not sufficient buffers to store the entire packets. Next we have an example of a store and forward mechanism. This is the time space diagram. In the time space diagram we need 5 cycles to store the entire packet at each location. 5 for 0th location, 5 for first, 5 for second, and so on. So in all we need 20 cycles to move our packet from node 0 to node 8 through 1, node 2 and node 5. The next mechanism is virtual cut through. Here the links and buffers are allocated to entire packet similar to stop and forward, but fleets can proceed to next hop before tail fleet has been received by the current router, unlike stop and forward, but only if the next router has enough buffer space for the entire packet. So the buffer demands remain the same. It also reduces the latency significantly compared to stop and forward mechanism, but it still requires large buffers and thus unsuitable for on chip. But as we can proceed, it reduces the number of cycles to move from node 0 to node 8 as depicted in the time space diagram. We can move from 0th node to first node on single cycle, and the remaining body fleets and tail fleet can follow us in a pipeline, and we can achieve the entire packet transmission in 9 cycles. In case we do not have sufficient buffers, the head fleet cannot move to the next hop. Hence, the entire packet stops or stalls at the location whichever the head fleet is. And when the sufficient buffers are available for the entire packet, then the head fleet moves to next location and the body fleets and tail fleets follow in a pipeline.